Okay, I'm going to start with the question. Why is glass so darn easy to break? I mean, look at the ultimate strength. 5,000 to 25,000 pounds per square inch. I don't know if you can tell how strong I am by the sound of my voice, but very strong. But seriously, I can't apply 5,000 pounds of force to a piece of glass, or 25,000 pounds, at least not to any sizable portion of the glass. And yet I can very easily break glass. I can take a sledgehammer that has a face of maybe a couple square inches and slam it into a piece of glass and easily break the glass. Am I actually applying a force of thousands of pounds? And look at steel. Steel is only a little bit stronger than glass, several times stronger than glass. Why is steel so much more difficult to break than glass? I can drop a piece of glass on the floor and it breaks. If I drop a piece of steel, the steel does not shatter. The answer to this has to do with the concept of energy. Ultimate strength alone doesn't determine how difficult it is to break something. That is, stress alone is not the full picture. It takes energy to break something. Not just a stress, but energy. At the molecular level, it takes energy to break the bonds between the molecules. And it turns out that the energy needed to break the bonds between glass molecules, which are typically silicon dioxide, is significantly less than that needed to break apart the iron molecules in a piece of steel. A measure of the energy required to break a square meter's worth of bonds is termed work of fracture, and it's typically reported in joules per square meter. Here we see the work of fracture of glass and mild steel. It takes from 1 to 10 joules to fracture all the bonds along 1 square meter of glass. That's not very much, which is why it's rather easy to break glass. Steel, on the other hand, doesn't require energy just a few times greater, but upwards of 1,000,000 times greater. Steel requires 100,000 to 1,000,000 joules per square meter. That's significantly more energy to break a piece of steel, and that's why it's much more difficult to break a piece of steel. Ultimately, breaking comes down to two things: the ultimate strength and the work of fracture. Now, for a particular sample of, say, steel, the energy needed to break the sample, however many square meters it stretches in cross-section, most likely a fraction of a square meter, that energy is called the fracture energy, also known as the modulus of toughness, and it can be found by finding the area under the stress-strain graph all the way up to the fracture point. So let me illustrate that on this stress-strain graph. And we'll say that this graph corresponds to steel because it does have the characteristic shape, more or less, of steel. It does not have the shape of glass, and I will draw the curve for glass later on, and we'll see it's quite different. Okay, so I filled in the area beneath the curve, and the area, whatever it is equal to the energy it would take to fracture the material. You could approximate the area using geometric shapes, for example, a triangle, a rectangle, perhaps a circle. To get an exact value, you would need calculus, and you would take the integral of the function. Let me label it for you. The area in blue is the fracture energy, again also called toughness or modulus of toughness. It takes more energy to break a material that's tough. Now, the energy that you put into the material by doing work in the physics sense on the material is stored within the material as what's called strain energy, sometimes called elastic potential energy. If you stress a material to its breaking point, the strain energy goes to breaking the molecular bonds one next to another, and the material breaks apart. That is, if you put in an amount of energy termed strain energy, that is equal to the fracture energy, the material will fracture. But what if you stop short of fracturing the material? What becomes of the strain energy? Well, the material will release it as the strain drops and the material relaxes. But you're probably wondering, where does it go? Well, it depends, but typically some of it goes into mechanical work, pushing on something and moving it. And the rest goes into thermal energy, and the material warms up a bit. We see that if we're beyond the yield point, the material has begun to deform plastically, and it won't return to its original length when the load is removed. It's permanently deformed. Let me illustrate what happens. Let's say that the material has reached this point. You remove the stress, or the load, right as necking is about to begin, and the material relaxes. As the stress is removed, the strain decreases, and the material returns to not quite its original length, but some new length that is some percentage longer than the original length, as indicated by the point at which you cross the x-axis. So we might end up with some strain of, say, 5%, which is now in a sense baked into the material. The material will never relax back to its original length, which was back here. Now, it turns out that the energy beneath this graph, this new line, is released by the material. So let me indicate that on the graph. Okay, I drew a line that's straight down, and now the area of this triangle, that is the area beneath this line, is released by the material. Okay, so I filled in this area in black. This is the energy that was released. I went ahead and made this portion white because for this particular example, we had stopped right here at this point, and this additional strain energy was never put into the material. What's in blue is energy that is dissipated as heat, energy that goes into thermal energy. We see no heating, however, if the material was stressed less than its yield point, which, as you'll recall, was right here. So if we had stopped short, for example, we had stopped at this stress, and the material had only been stressed up to this point, and then we removed the stress, the material would return to zero strain, back to its original length. If we plotted the points, as the stress diminished and the object returned to its original length, those points would lay on top of the original points of the graph. And furthermore, if we found the area beneath this new curve, it would be equivalent to the area beneath the original curve. That is, the black triangle that we would draw here is equal to the blue triangle that was here. So the energy released is equal to the energy that was initially put in, and none of the energy goes into thermal energy. We see no heating. All the strain energy is now used to do work on something. For example, the strain energy in a longbow could be used to push an arrow forward. Now, most real examples of objects storing strain energy, including the longbow just mentioned, are not simply in tension, as you might find in a testing machine, but they are either in compression or maybe both, though not obviously in the same place within the material. That is, parts of the material might be under compression and parts of the material in tension. If you think of a spring, a metal spring that's not tightly coiled when it's in its relaxed state, you can store strain energy in the spring either by compressing it or stretching it. In both cases, it obeys Hooke's law, and most materials are the same way. However, we're going to avoid further discussion of compression, at least for now, to simplify the discussion. But let's stick with the longbow for a bit longer. Here's a picture of a longbow. Consider a person pulling back on the string, bending the bow. The bow starts off straight, and as a force is applied, it bends. And the bent wood is storing quite a bit of strain energy. Work is being done on the bow in the amount of force times distance. The work on the bow is equal to the force applied to the bow times the displacement of the bow. An understanding of Hooke's law will convince you that the force varies, and in this particular case we can be specific and say increases as the bow is drawn, increasing from value 0 up to some maximum value. Thus, to obtain an accurate measure of the work done on the bow, one uses the average force. As the force began at 0 and ramped up to F, the average force would be the average of those two numbers, 1/2 F. And so up here we notate that this force must be the average force, which is equal to 1/2 times the maximum force. I'm going to avoid putting the tag maximum on here, but that's how you should interpret this, times the distance or displacement. Technically different things, but here we'll treat them as the same thing. So as I've done in a previous video, I'm going to switch over from F to P to indicate the load placed on the object, and from D to delta to indicate its extension. And I'm going to say that the work done is equal to 1/2 times the load times the extension. Work is a measure of energy transfer. Thus we can say the strain energy given to the bow is equal to 1/2 load times extension. The strain energy per unit volume is simply this quantity divided by volume. But volume is cross-sectional area times length. And what we find here is that load over area equals stress, and extension over original length equals strain, and the work done per unit volume is equal to 1/2 times the stress times the strain. If we go back to our graph, this should all make sense. What's the area of this triangle? 1/2 base times height, which is what? 1/2 strain times stress. The same thing that we just worked out while considering the work done. Furthermore, as Young's modulus, or the modulus of elasticity, is equal to stress over strain, we can modify this equation to obtain some additional information. We say that the strain energy, at least while we are in the elastic portion of the graph, is equal to 1/2 stress times strain. And we can multiply this expression by something that is equivalent to 1, and that won't change the equality. So what I'm going to do is I'm going to multiply the numerator by another sigma, that is by stress again. And I'm going to place a sigma in the denominator as well. Okay, so I've made a change to this expression, but it's equal to the expression I had written down just a moment ago, right? Because I can just cancel out a sigma and return to my previous expression. Now the reason why I'm doing this is to show you that this can be rewritten as 1/2 times stress squared divided by elasticity. Writing it in this fashion highlights a relationship between strain energy and stress. It says that strain energy is proportional to the square of stress and inversely proportional to Young's modulus. That is, if I double the stress on a material, the strain energy quadruples. If I triple the stress on a material, the strain energy goes up by a factor of 9. Regarding the elasticity, if we double the elasticity, or the steepness of the slope of our line, the strain energy becomes 1/2 of its previous value. It's now time to look at the graph for glass. The stress strain curve for glass looks something like this. And that's it. It's very steep, meaning that it has a very high Young's modulus. It takes a lot of stress to get just a little strain. It's linear until the end, meaning the material deforms elastically until it breaks. If you stretch this material out and then remove the stress prior to breaking, the glass will return to its original shape, and all of the energy that you put into it will be released. None of it will turn into thermal energy. But notice the area beneath this graph. It's rather small. Let me illustrate that. Okay, so I filled in the area beneath the graph in some reddish color, and this represents the strain energy stored in the material, and we can see that it's not very much. For a high value of E, when E is large, the strain energy is correspondingly small. And that's why glass is so easy to break. It can't store much energy, unlike carbon steel, which can store quite a bit of energy. Let me give you one more term before we stop. The area beneath the linear portion of a stress strain graph, whether it's for glass or steel or any other material, up to the yield point, that is, the area beneath just the elastic portion of the graph, the amount of strain energy that you can put into the material up to the point where it can no longer deform elastically, is called the modulus of resilience. So let's write that down. And as long as the material is within that portion of the graph, it is resilient. It will return to its original shape when you remove the load. And as a reminder, the area beneath the curve all the way till the very end, the area beneath the curve up to the fracture point, which might be the same as the modulus of resilience, but typically won't be, is called the modulus of toughness, or the fracture energy.